Okay, suppose I have two finite dimensional linear spaces with the same scalars. They're isomorphic if only if they have the same dimension. Let dimension v equals n, dimension w equals m, where v and w are linear spaces. So I have two finite dimensional linear spaces, and let's suppose they have the same scalar. I'm going to prove they're isomorphic if and only if they have the same dimension. So this means I have to prove two things. Suppose v and w are isomorphic. Then, by definition of isomorphism, there is an invertible linear transformation T that goes from V to W. By the fundamental theorem of linear algebra, the dimension of the kernel of T plus the dimension of the image of T equals the dimension of the set of inputs. Set of inputs is V. But if it's invertible, that means it's one-to-one and onto. If it's one-to-one, that means that the kernel is just the only element that's in the kernel is 0. That means that the dimension is 0. Since it's onto, that means that the image is all of W. So that means that this is the dimension of W. And so that tells us that if they're isomorphic, then the dimension of W equals dimension of V. So we proved one direction by just using, we'll use it quite a bit actually. We use the fundamental theorem of linear algebra. Then we use the fact that T is, the definition of isomorphic means there's an invertible T. Then we use invertible as the same as one-to-one and onto. One-to-one means that the kernel is just one element, the 0 vector. The dimension of just the 0 vector is 0. And we use the fact that onto means that the image is equal to the codomain. And so that means the image of T is equal to W, so I get that. Now suppose dimension V equals N equals dimension W, and let V1 up to Vn be a basis for V. I know that there are n things in there because that's the dimension. And W1 to Wn be a basis for W. Now I'm going to define T going from V to W by T of V equals T of A1 V1. So first, any element of V can be written as a linear combination of the basis because the basis spans. And I'm just going to define this to be so I'm using the fact that the basis spans in here. So take however you have V and write it in terms of the basis. And now all I'm going to do is replace, what T does is just replaces the basis elements, the VI's, with WI's. This is linear. Suppose you have T of A plus B, that's equal to T of, how about A1 V1 plus det plus AN Vn. I'm being a little sloppy with my defining stuff. I'm just kind of defining stuff verbally. So suppose that A can be written as a linear combination of the base elements like that and B like that. Well, that's equal to T of A1 plus B1, B1 plus det plus AN plus BN, BN. By definition of T then, this is just A1 plus B1, W1, plus Z plus AN plus BN, WN. But I can separate all the A's out. AN, WN. And I can separate the B's out. Z plus BN, WN. But this would be equal to T of A, and that would be equal to T of B. So it's looking good for linear. Also, T of, let K be a scalar, I'm saying it verbally because I'm lazy, that's equal to T of K times A1 V1 plus Z plus AN VN, distribute a K through, K A1 V1 plus Z plus K AN VN, which equals K A1 W1 when I get rid of the T, plus KAN WN, but I can factor out a K out of all those, A1 W1 plus that plus AN WN. And it's not much work to show that this is equal to K times T of A. So T is linear. But I'm not done. I can't just have a linear transformation. I have to have an invertible linear transformation. So I think I might need to go to the eraser here. Or, in other words, as I like to call it, Control V. Control Z. So I'm just going to back up. Or maybe I can do it. Maybe I'll prove as onto. Let a generic element of W, consider a generic element of W. Well, W has a basis like this. So I can define A1 W1 plus AN WN. This really is a generic element of W. So I can, it's pretty clear that I can let A1 V1 plus AN VN is going to equal my generic element. So I guess onto. Why do I know it's 1-to-1? Well, this comes down to the fact that bases are linearly independent. Let's suppose that T of A1 V1 plus AN VN equals T of B1 V1 BN VN. Well, I'm just going to slide everything over to one side. I think I can do this. B1 V1 BN VN equals 0. But 0 is equal to T of 0. So I can combine these two together by doing T of A1 blah 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 plus AN VN minus this whole thing. And if I combine that, I end up with A1 minus B1 no. Let's even simplify this. Let's simplify this. So I'm going to show us 1-to-1 by just showing that this thing has to be in the kernel. That the only thing in the kernel is the 0 element. So if this were true, this is getting messy, I'm sorry. So if I have T of A1 V1 AN VN equaling the 0 vector of W, I'm going to show that this thing has to be 0. Well, this thing is equal to A1 W1 without the T, AN WN equals Z. And since the basis W's are linearly independent, A1 equals A2 equals AN equals 0. So the kernel